All right, so we're going to talk about the polynomial version of Euclid's lemma. So a quick definition first. We say that two polynomials, so again, these are polynomials, over a subfield K of C with GCD equal to 1 are coprime, or F is prime to G, or F and G are relatively prime, all of these things are the same thing. So coprime I'll probably say most often because it's shorter, and then of course F and G are relatively prime, we might also say if that's much longer. But all these things all these mean the same thing. Okay. So what is the polynomial version of Euclid's lemma? Well, again, let's let K be a subfield of C. And irreducible polynomials kind of play the role of prime elements in the polynomial ring over K. So what does Euclid's lemma say? Euclid's lemma says if a prime divides a product, then it divides one of the terms in the product. So what are we going to say here? If F is an irreducible polynomial over K, G and H are polynomials over K. If F divides GH, then F divides G, or F divides H. Okay, that's our polynomial version of Euclid's lemma. Proof. Well, if F divides G, we're done. Otherwise, F doesn't divide G, and we show F divides H. Great. The GCD of F and G is 1. All I'm saying is the GCD is a non-zero constant. The GCD is only unique up to a constant. You can always divide by the leading coefficient to make it 1. Why is this? Well, F doesn't divide G, and since a GCD must divide both, well, let me say this slightly better. Let me just say as if D is the GCD of F and G, then D divides F. But F is irreducible. So the only terms that divide it are multiples of itself and constants. So D is either 1 or D is F. Up to a scalar, we can assume that D is 1 or D is F. But if D is F, D is also a divisor of G because it's the greatest common divisor of both of them. So D divides G, but D is F, so F divides G. And we are assuming F does not divide G. So the only other option is that D is 1. All right, great. So D is 1. Now let's let A and B be Bezout coefficients for the GCD of F and G. So that means that the GCD, which is 1, is equal to AF plus BG. All right, now what we're going to do is we're going to take that and we're going to multiply through by H. If we multiply through by h, we get h is HAF plus BGH. The order of multiplication doesn't matter because we're commutative, so I'm just associating like this. But F divides GH, so there exists some C such that GH is CF. So this tells us then that H is HA times F plus B times CF, or equivalently H is HA, oops, let's factor out the F, doesn't matter the side, but I'm going to put it on the right. That tells us that F divides H. And so this polynomial version of Euclid's lemma is saying that irreducible polynomials kind of play the role of prime elements. And we really did need a field here because we needed access to Bezier coefficients, and we're talking about those sorts of things. So that uses the Euclidean algorithm, which requires a field and so on. But nevertheless, this does hold. And this proof also, we were able to really see Bezier coefficients come in and play an important role. It made the proof very, very simple, the existence of these Bezier coefficients.